A limit is the value near a point of a function. Limits can be evaluated graphically, analytically. In most cases, solving a limit analytically is the best way to go. First, we need to understand how a limit is read. For example, take the following limit. The limit reads, the limit as x approaches 0 of the function 3x plus 1. Now that we know how to read the limit, we need to know some basic rules. The first basic rule is the limit as x approaches c of b is equal to b. The second basic rule is the limit as x approaches c of x equals c. And the third basic rule is the limit as x approaches c of x of n equals c of n. Now that we know some of the basics, we can learn some properties. For all properties, let b and c be real numbers, and let p and q be a positive integer where q does not equal 0. Let f and g be the following functions. The limit as x approaches c of f of x equals L, and the limit x approaches c of g of x equals k. The first property is the power property, which states that the limit as x approaches c of f of x raised to pq is equal to L raised to p over q. Next is the quotient property, which states the limit as x approaches c of f of x over g of x is equal to L over k when k is not equal to 0. Following the quotient property is the product property, which states that the limit as x approaches c of f of x times g of x is equal to L times k. We must also look at the sum or difference property, which states that the limit as x approaches c of f of x plus or minus g of x is equal to the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x, which equals L plus k. Finally, we must look at the scale and multiple property, which states that the limit as x approaches c of b of f of x equals b. Also, this means that the limit as x approaches c of f of x equals b times L. The first step in solving a limit is plugging in what x is approaching and see if there is an answer. This is seen in example number 1, where the limit as x approaches 2 of x squared plus 5 is equal to 9. When you plug the 2 in, you simply solve and get your answer of 9, and you're done with your work. Now the question is, what happens if you get 0 over 0? That means that a function agrees at all but one point, which means that there is a hole. In example 2, you plug in the 1 for your x, and you get 0 over 0. But you can't have 0 in the denominator. So, you must solve the limit by taking out x minus 1 and solving it after that. Now another question arises. What do you do when there is a radical and there is a denominator of 0? An example of this is seen in example number 3. You use the conjugate, but you don't distribute the x because it makes it easier to cancel out in the end and get a final answer.